Is can you see my screen, Dr. Rajaram?
Yes.
Okay. Can I start?
Yes, you can start.
Okay. Thank you very much. Thank you very much for giving me an opportunity to speak. I'll be talking about a feasible retrofitting solution to the soft story problem by using a socio-technical approach. And this work was carried out by one of my students, Mr. Kishore Timsina, who's now working in Nepal. And wholly this work was developed in the premise of earthquake damage in Nepal in 2015. So to start with, I would like to describe my trip to trip to Nepal after Gorkha earthquake. So the name of the earthquake is Gorkha earthquake, which happened in 2015 in the month of April, and I visited Gorkha in 2016 June. So almost after one year and 2 or 3 months, I visited Gorkha to do a field study for my PhD as well as for an organization called JRapid to understand the condition of buildings in Nepal in the aftermath of a major disaster. So with with an objective of studying buildings which were damaged of this type and using sophisticated equipments to understand the dynamic behavior, we went to Nepal, and our basis was to collect samples and bring it back and test it in our heavy structures laboratory. And we were also thinking of developing some large scale simulations for Nepal at that point of time. In that process, we saw some very interesting practices and very interesting awareness programs conducted by an NGO called NSET for the rehabilitation and retrofitting and creating awareness related to earthquake resistant structures in Nepal. And what we can see here is a very small shaking table, a very small shaking table here, and a very small building with perfect lintels and bands. Um, and what was being demonstrated here it cannot represent any heavy structure laboratory, but what represents here is is the complex explanation in a very simplistic manner. So two persons need to pull and push this shaking table, and then you can see that a building which has good seismic resistant features performs well, and the building which does not have would have collapsed. So this kind of very simple explanation fascinated all of us. And we also saw that they have provided retrofitting solution for gable wall constructions by using simple gable frame, and how this could be effective. And they also demonstrated on um, s- how structural detailing should be done in in residential buildings with proper detailing, such as 135-degree bend of stirrups, etc. So from here, what we learned is, in spite of the fact that all these training centers were located in rural places, they were able to create a huge amount of impact. And what I personally learned from here is that even if we learn hard, if we cannot keep it simple and educate, the implementation process is very largely affected. And with this understanding, my approach of doing research had slightly changed, because the purpose and objective should be to solve the problem. And for that, we need to understand the problem thoroughly. In this case, In this case, the Nepal NGOs and the government, they understood that their problem is economy. They cannot afford huge amount of money to create awareness in rural areas. So therefore, they created the equipment small, but the science and engineering behind it remained the same, but they right-sized the understanding of science and engineering to the fit into their budget, and then they could use this program to create awareness even in small areas. So this was something that I understood a lot, and from this is the motivation behind the research work that I'm going to talk about from now on. And just to give you a brief preface of today's presentation, the field of interest here is structural dynamics and earthquake engineering. And of course, we will also talk about some social aspects involved in retrofitting. Retrofitting is strengthening an existing building against earthquakes. And this research work is theoretical, field survey, and we have also done numerical. And this is the whole work was developed in the context of Nepal, which means that Nepal acts as a laboratory for this research work. However, it is also applicable for seismic zones of India, where this soft story problem prevails. I'll talk about soft story problem in the next slides. As and it I basically assume that the audience could understand some basic structural engineering terms such as interstory drift, finite element method, static pushover analysis, base shear and roof displacement, dynamic analysis, and engineering optimization. You don't have to know details of these technical terms, but at least a broad understanding of what these terms are, and what are their implications would be enough for understanding my presentation today. And the numerical modeling is done mainly using a tool called applied element method. So you can get more information about this tool from your faculty, Dr. Rajaram. He's also working in this. He's also working on this tool, and I think some of you are working in your final year thesis as well. So just before I go into this, so during my visit to Nepal, when I was going through the suburban areas, the areas which act as town centers for rural areas, looked somewhat like this. And during my visit, what I noticed is all these buildings. So there is a narrow road which is passing through this town, and you can see buildings which have open stories almost everywhere. And as a structural engineer, as a person working in earthquake engineering, what we think as soon as we see these buildings is, of course, there are a lot of other problems with these buildings. There are a lot of other provisions which does not exist, but soft story problem is a major problem, and many buildings had collapsed due to uh, soft story uh, soft story problem in one second. Yeah. So there are many other problems, including other than soft story problem, but this soft story problem has caused severe damage during Gorkha earthquake, and many buildings had gone into pancake collapse during Gorkha earthquake because of soft story problem. And this is a very prevalent and very well-known problem, yet this has not been solved. And I was wondering what would have been the reason, even after 1.5 years since Gorkha earthquake had occurred, people were not retrofitting their buildings. So as a structural engineer, I would think that they are just not worried about their buildings. They have seen so many buildings collapsing because of this problem, but still they have not retrofitted it. And somewhere I was roaming around and I was trying to learn about the society, and I had interview with people, and I was seeing that people do not get enough incentives from the government to conduct retrofitting, and even if they get some incentives, they are not enough uh, to incorporate the solutions that are already available. Of course, we all know that there are enough solutions which are available to solve this soft story problem, yet it has not been implemented. So I was wondering what would have been the reason why this implementation didn't happen. So one thing that I thought was maybe people didn't know. Yes, definitely people didn't know about the threat of earthquakes for a soft story problem. But then they had Gorkha earthquake, and in certain aspects they know better than me, or they know better than researchers in certain aspects. Then how can we say that they don't know about soft story problem? Yes,
Well,
maybe people who who have not experienced this Gorkha earthquake might think that yes, this this soft story problem is something that we don't care about. But most
uh,
of them would know, at least 30 to 40% of the people would know this soft story problem. But still, retrofitting was not being done. Then I started exploring into the available solutions. When I
well,
explored available solutions, we found that these solutions were somewhat like closing their open space on their ground floor. So
well,
these solutions, which would ask these landlords to close their shop.
well,
Hello.
well,
Hello. Okay. So we saw that these open
trial,
spaces would be closed because of the solutions. And we saw that all these buildings are open because of shops or parking lots.
well,
And, and asking these landlords to just close their livelihood does not make sense, because
well,
probably the reason why these buildings exist in this region um, is along this
well,
mountain road is because it is a source of livelihood for these people. So asking them to close their shops at this point because of a
trial,
plausible disaster in future is not a solution
trial,
which is customized for them. So then we decided to explore some solutions which might
trial,
allow them to continue their business as well as um, excuse me, does somebody want to
trial,
ask me something?
So you already you
trial,
all the participants, so some students is going on, you are writing this out. Okay, so you can carry on.
Okay, so we were looking at solutions which would keep their shops open yet provide a retrofitting solution. But then those solutions are like providing steel jackets on the ground floor, or providing some expensive fiber reinforced metals, or fiber reinforced polymers to wrap the building so that it can provide certain amount of life safety. But what we understood is these materials are insanely expensive at this point of time, and finding a solution in this um, area would be a lot more expensive and would be time consuming to even reduce the cost of the material by large scale production, because Nepal is not an industrial country. It largely depends on India and China to acquire certain raw and processed materials for construction. So we need to provide solutions which are customized for their usability. So with this, I actually go into my core part of the presentation, which would be divided into the components that are shown in the status bar below. So coming to the background, fundamentally, the buildings with shops is our primary concern, and the buildings with parking lot is our secondary concern. So there might be other reasons because of which soft story problem would be existing, but we would be restricting to these buildings which are predominantly existing in urban and semi-urban areas of Nepal, which is a country with huge amount of seismic threat. And what happens to this soft story is the stiffness of the bottom story becomes lower than the stiffness of the top story, and because of which there is something called as P delta effect. When the building slightly moves, the whole mass on the top floors would exhibit moment at the bottom of the building, and this building goes into a mechanism and gets collapsed. And that's what we have seen in 2015 Gorkha earthquake, where many buildings collapsed in the pancake collapse mode. And preventing these buildings to collapse in this way would be the primary concern of this research. So, but then if we if we see like a structural engineer, we have so many buildings with open stories in almost every semi-urban urban areas of Nepal, is because of the economic condition and the amount of benefits that they get because of these areas. It is probably their livelihood. The reason why these buildings are constructed in urban and semi-urban areas is because they earn livelihood from these spaces. So the question still remains why. So the reason is because of the social need. It is their culture and lifestyle to have business and parking on their first floor or ground floor. Um, so because these buildings are usually constructed in urban and semi-urban areas, and the social problem is that there is no enough economical support from the government to go for retrofitting, and the promotion system does not exist. Is the social is comprises into social need, and then the technical need is appropriate methodology which can solve this problem, and the availability of material. We cannot impose solutions like steel jackets, etc., because steel jacket is definitely a very good solution which can also retain their open space, because steel jacket is only going to jacket the columns, and the space required for opening the shop still remains open. So this is a good solution, but unfortunately, these the number of shops or the number of buildings which are open are huge, and we need a huge amount of steel, which is probably not available indigenously in Nepal. It has to be imported from India or China, and the cost of retrofitting will become very, very high. And considering that this is a very large scale retrofitting project, probably this cannot be a good solution. So what we understood is that the soft story problem is due to business space or parking area in RC frame buildings. So we are narrowing down the problem by saying that it is because of business space and parking in RC buildings. For to actually validate or verify our hypothesis, what we did is we took up this is the map of Nepal, and the places which are marked with a star are the places where the provincial municipalities are located. We conducted an online survey to understand about the problem principally. And for that, we consulted about 35 professional engineers working in 20 different municipalities across Nepal, who are responsible for design and construction of these kind of buildings. And from their responses, we understood that there are more than 45% of the buildings which have shutters on their ground floor in a year, and the average number of stories of these buildings are less than 3, most of them. So this is a mid-rise building. These are mid-rise buildings, and the purpose of this open story is either for business or residence also, in certain cases where people would have a small parking lot in the front and then a very small room in the back. And why they are not going for retrofitting is because they do not want to retrofit and close their business or parking lot. Of course, this is a very natural understanding based on our observation, but still we wanted to validate it by using the responses of professional engineers. So the hypothesis was kind of verified with this point. And then the awareness is quite low in Nepal, in spite of the fact that there was Gorkha earthquake already. And what is the requirement of these people? So now we try to educate them. If we try to educate them on retrofitting of buildings, what would they ask for? Do they ask for life safety, or do they ask for a very, very strong building? So the answer was they want life safety during large earthquake. That is, even if the building goes into collapse mechanism, you have enough time to evacuate the building completely. It wouldn't be a sudden collapse. So that amount of safety, if you can ensure with your if you can ensure with your retrofitting solution, would be a great solution for their social need, considering their economic status. So after that, we did a technical survey. And to do technical survey, we used software called AEM. So what we did is we took a very typical frame, which is shown in A, and we took this frame and we applied a force on the top story to replicate a pushover kind of behavior from the building. And we pushed this frame and we tried to get the force and displacement delta, and we divided the force by seismic mass, and we got something called as base shear coefficient as shown in this figure. So we did this exercise with all the frames shown in this figure. These are different kinds of frames or different kinds of solutions that have been implemented in the past. So the best solution would be using an infill wall itself, which is in B. And then we use solutions such as strengthening all the columns and beams, strengthening all columns and beams of open floor, strengthening columns only, strengthening columns and increasing shear capacity of beam, increasing capacity equal to infill, increasing the column capacity, which would be equal to the infill, and then providing steel bracing, providing shear wall, and steel jacketing. So from these solutions, we derived certain conclusions, and they are shown graphically here, where we have compared RC shear wall, which has very high capacity, soft story, which has very low capacity, and infill wall, the one which is here, B, has the optimum or ideal capacity, which would be which would protect the building from going into a soft story collapse mechanism. So what we decided to do is, I'll explain it in the next slides, but to briefly tell you, if this is the capacity of your soft story, if you can increase the capacity of soft story to this point by bringing down the capacity of shear frame to this point, would be a very optimum method of finding a retrofitting solution for soft story problem. But among these different cases of retrofitting solutions, we drew a few conclusions based on analytical methods as well as numerical modeling in applied element method. We found that these 5 cases were showing low performance. Some of them are very high in cost. Some have very low material availability, such as steel jacketing, as I explained earlier, is not available in Nepal, and the cost is also very, very high. And some of them have very low usability. For example, this is a very ideal case, and this has very high strength. And both of these cases have no usability. Suppose you suggest one of these two as solutions, the landlord or the person who is running a business on ground floor would not be able to run his business. He has to close down his business. So that is not a solution at all. So the objective of this research is to provide a practical and feasible solution by ensuring adequate performance, cost, usability. And we will do this in applied element method and by using optimization algorithm. So if you can optimize your performance by keeping in mind of the cost and usability, you will provide a very customized solution for people of Nepal. So this was the objective, and how to do this is by developing an optimization methodology for reinforced concrete infill by ensuring performance, cost, and usability. And for this, we needed to modify this applied element method tool to incorporate this optimization algorithm. And then finally, in this study, we have also developed guidelines for design and implementation of this method. And coming to the fundamental question, how we do this? So this is the frame. And what we are saying is, in the previous slide, you would have seen that the frame with shear wall had very high strength, which is not really needed. So we have decided to open up this shear frame gradually to match the performance of a frame with masonry infill. So shear frame is an infill with so this shear frame infill is an infill with concrete. If you reduce it so that the remaining amount of shear wall can replicate a full infill inside this frame, would be a very good solution. And for that, we needed to do a mathematical optimization. So you gradually open it and you ensure performance, cost, and usability, all 3 parameters. You will get an optimized frame which will perform like a frame with masonry infill. So this would be a good solution. And how did we go about it is what I will explain in the next methodology part. And to do this, first we needed to understand the problem thoroughly. And for that, we had to do technical survey, literature survey, and social survey. And we have done this technical, literature, and social survey already. And briefly, the results were presented to you in the previous slides. And now the current work is to develop an optimization framework. So what is an optimization framework? Optimization framework is like minimizing or maximizing an equation. And here what we are doing is we are minimizing or maximizing with consideration to certain constraints. So what are we minimizing or maximizing is we are minimizing the cost of retrofitting subject to certain restriction on performance, usability, and complexity in making this retrofit. Suppose I provide a solution in which you just have to make some spherical cuts inside the infill area. So that kind of complex construction might increase the cost and might also make it impossible for the local masons to execute this kind of retrofitting solution. So that would be really difficult. So keeping in mind of the fact that the cost should be minimum, yet the performance should be adequate, yet the usability should be adequate, and yet the complexity should be low. By keeping this in mind, we developed an optimization framework, and to see whether this optimization framework would work properly or not, and to get input values for this algorithm, we needed to do some field study. And we also needed real building parameters to carry out the numerical modeling of um, of the proposed solution. So this whole part constitutes this development of optimization framework, and field study constitutes the core methodology of this research work. And then we went for numerical analysis in applied element method. So what we have to do is incorporation of this optimization framework we developed into applied element method, and then verify it with a few case studies, and then conduct dynamic analysis to check whether the solution frame or the resultant frame which has been extracted from this algorithm is good or not. And then finally we propose implementation guidelines and design guidelines, and we also propose how this method can be brought into practice. And coming to optimization, for optimization, first we take a bare frame, we take a frame which has an open story, and we check whether this frame is actually a soft story or not. So we check the initial capacity of the frame. Usually the frames which are not seismically designed or are usually soft story. And then we initialize with various parameters such as opening dimensions, the diameter of rebars to be used in the retrofitting, the spacing of rebars inside this retrofitting part, and the thickness of the wall. And then we gradually go into the cycles of iteration. So the optimization algorithm used is sequential quadratic programming, and this is a type of numerical optimization problem, numerical optimization methods, which was developed back in 1980s and 90s. And we found that this is very suitable for our requirement. And so we use this, and in which we considered an objective function which will minimize the cost of retrofitting, or minimize the cost of the construction for construction inside the open frames, which is here. And the cost depends on the concrete cost, reinforcement cost, labor cost, and the business disturbance cost as well. Suppose you go for construction, you have to close your business for a few days, and the business disturbance cost is also considered here. So if you keep the complexity low, the construction time will also be lower. So adequately, we developed some empirical equations, or we proposed a few empirical equations to calculate all these costs. And the constraints used in this optimization are performance constraints, so which is the fundamental constraint. So as I said earlier, if the stiffness of the bottom story is lower than the stiffness of the higher stories, then the building has a tendency to go into soft story mechanism. So this thing has to be avoided. So what we did, you keep opening the shear wall to a point where the stiffness of this floor becomes equal to the stiffness of higher floors. So that was the performance constraint. And then usability constraint would consider the business constraint and parking constraint. So for business, you need a sufficient amount of opening to run your shop. For parking, you need a sufficient amount of space so that your vehicle can be inserted inside. So this is also a constraint that has to be fed into this algorithm. And then complexity constraints largely depends on what is the shape and what is the radius of the opening. So this was also considered in this numerical modeling. And finally, where do we stop opening this frame? So we stop opening it when the global performance constraint is satisfied, which will be explained in the next slide further on. And we keep on iterating again and again. And finally, we come to a resultant frame, or a frame which is considered to be a solution frame, which would be free from soft story problem. So this is the final optimized frame. When you achieve convergence, you get this. And to give a little bit more information on how these objective function and constraints and the global performance are calculated, it is shown here. So it's a cumulative sum. The objective function is a cumulative sum of material cost, labor cost, and disturbance cost, as mentioned earlier. And the performance is nothing but the stiffness of adjacent story is said to be lower than the stiffness of soft story. So it becomes a pyramid kind of a structure in terms of stiffness. So that would be considered as a very stable structure against soft story problem. And our usability constraints are based on the amount of area that has to be opened. And here the landlord can give his required area, and our algorithm can set that requirement, and we can propose a solution in that context. And finally, the complexity constraints has considered various variables to consider the complexities in the opening, complexities in formwork, etc. And we set a particular requirement empirically by using expert opinions. And we have also done a field study, which will be explained later on, in coming up with different variables which were used in setting these complexity constraints. And finally, in AEM analysis, we also check the performance. And to check this performance, what we did is we developed a new index called relative softening index, which is nothing but a ratio of time period of filled of our retrofitted frame by the time period of this infill frame. And we set that this shall be less than or equal to 1, which is nothing but we are trying to equate the time period of this frame with the time period of this frame. But at what point? So we push both of these structures. So that the interstory drift, the drift that this building has achieved, will become equal to 0.75%. So for Nepalese building, after Gorkha earthquake, many experts visited, and they said that 1% drift is enough for these buildings for collapse and etc. So these were expert opinions. And since we are doing a numerical study, we wanted to have a more conservative method. So we restricted our drift at 0.75% itself. So let's say when these two buildings are pushed and we take push to a point of 0.75% drift, and the time period of these two buildings will also increase gradually as damage occurs, because you're pushing the building, and 0.75% drift is adequate damage, and these time periods will change. We take the ratio of these two time periods. We're saying that we are equating the time periods of these two buildings at 0.75% drift. So it's quite a conservative way of stopping our numerical simulation. This we did. And finally, we had to implement this in applied element method. As I told you, applied element method is a different numerical tool which can conduct collapse analysis, and it has proven to be very efficient in capturing the behavior of reinforced concrete and masonry buildings in the past. And your faculty, Dr. Rajaram, knows it very well. And if somebody who is interested in learning about it can contact him. So in this, there are different stages, like in finite element method, there are different stages of providing input and then setting up stiffness matrix, inverting them, and getting displacement solutions and satisfying compatibility equations, etc. So in this process, so we initially set our baseline input frame, and then we set a baseline input for infill RC, and that is inserted inside applied element method. So this applied element method has been developed in Fortran. So we had to develop a few Fortran algorithms to insert this optimization scheme into it. And as I mentioned earlier, we used SQP, and this whole setup was inserted carefully without disturbing the existing structure of applied element method. And this is a brief understanding of what this applied element method is. It's very similar to finite element method with stiffness matrix, compatibility equation, constitutive equation, and equilibrium condition. The fundamental difference is that in finite element method, your forces, displacement, stress, strains are transmitted at the nodes, but here we have springs where the elements are in the form of square, are in the shape of square, where these square elements do not deform, and all the deformations are taken care by the springs, and they use same stress strain and shear stress shear strain material models, like in case of one-dimensional finite element method. And since due to time limitation, I cannot explain further about this. But if someone is interested in learning about it, he or she can contact me or Dr. Rajaram in how to learn about this tool. And coming to the field study, we conducted a field study with the fundamental objectives of verifying our assumption and to extract properties of existing soft story buildings, and finding the cost of material, labor cost, the business disturbance cost, and the optimization parameters such as cost, usability, and performance had to be discussed practically with different stakeholders in Nepal. And we also needed to show how this can be designed or constructed, and what would be the implementation strategy for this new retrofitting solution. So for that, we conducted a field study. So we went back to Nepal again, and in the form for survey, we created a mason survey plan, engineer survey plan, and house owner survey plan, and building assessment plan. So all these questionnaire forms were developed particularly for this research, and they are quite universal and can be used for other purposes, and can also be used for our Indian buildings in capturing and using it for different kinds of details. The type of survey we followed was questionnaire survey, interaction and discussions, and building assessment and material tests. In the actual survey, we interviewed 57 masons, 20 engineers, 17 house owners, and we tested about 14 buildings with rebound hammer and ultrasonic pulse wave test to get the current material property of these buildings approximately. And the study analysis showed that most of these buildings were used as rented shops, and many people didn't know about the soft story problem, and people don't want to close their shop due to retrofitting, and people can spend about 10 to 15% of their total building construction cost on retrofitting. Let's say if the cost of the building is 20 lakh rupees, people are ready to spend about 2 lakhs for retrofitting. So that was on a very positive note, that people are willing to spend a little bit more money than we thought of. And this was probably due to the Gorkha earthquake, which happened in 2015, and the amount of awareness programs that were conducted in Nepal in the aftermath of Gorkha earthquake.
And we also examined the different costs of materials used, and those were given as feed-in data for the optimization algorithm. And what we also understood about preferable performance of these buildings is that people want life safety in large earthquakes. As in the first engineer survey also, we got the same kind of response. And the average business opening, the width of the shop right now is around 3.45 meters, but people are willing to give away about 1 meter, and they want to have a minimum opening length of about 2.5 meters. So this was also a very positive response from the landlords, that they are willing to provide about 1 meters, or they're willing to sacrifice about 1 meter for retrofitting their buildings. And we surveyed on different geometrical configurations of what beam sizes are used in Nepal, what kind of rebars are used, and what stirrups are used in Nepal currently. And we got the mix ratios and the compressive strengths of buildings from the field tests we conducted, and the thickness of the walls that are currently used are about 9 inches approximately. So with these inputs and these different parameters, we started conducting our numerical modeling in AEM, the actual numerical modeling. And the final inferences we got from this field study is that the soft story problem is a socio-technical problem. And the solution to this problem should be cheap, but at the same time, there should be usability. And the performance level required for these buildings is not an extraordinary retrofitting solution which will be fail-proof in all cases of earthquakes, but they want life safety in large earthquakes. The opening size currently is 3.45 meters, but they only want 2.5 meters. They are happy with 2.5 meters of opening space. And the building properties are usually uniform in different places based on our amateur survey, because what we understood is that usually the mason class are very well connected and they construct buildings very similarly. The engineering construction is not a common practice in the suburban areas of Nepal. So coming to the analysis, we took 3 different cases with different kinds of material properties and dimensions, which are shown in the other tables. So this is case 1 is a typical soft story frame with 1 bay. Case 2 is a typical soft story frame with 2 bays. And case 3 is not a typical frame, but we have seen these kind of buildings which had collapsed in Nepal Gorkha earthquake. So there was a hotel in I think Dolka region of Nepal where the first floor, the ground floor was not soft story, but first floor had a conference room with glass windows. So that is actually a soft story where the stiffness of this floor is lower than the stiffness of this floor. And this building, after the earthquake, this whole floor had collapsed in the pancake collapse form. So we consider all these 3 cases, but today I'll be showing the results of case 2 only, which is quite a typical frame. And we use the following properties. The details of the properties can be learned later. And what we did the iteration. We took this open frame first. And then in the first iteration, we filled the frame with a shear wall. And gradually we started opening the wall. And whenever we open, we push the frame. We keep on pushing it. We do a pushover analysis. And we try to balance this floor stiffness with this floor stiffness, and we change different properties in the iteration. In that iteration, we change the dimensions of rebars, spacing of rebars, and everything, so that the stiffness of bottom floor will match the stiffness of higher floor. And we keep on doing it until the point where TF becomes equal to TF infill, as I mentioned earlier. So at this point, we stop the simulation. So we consider that as the convergence point. So you can see that the final frame, which was obtained here, and the frame, which is in iteration 1, has this final crack pattern in this figure. And here you can see that this shear frame has not cracked as much as the cracks in the top floors, is because in the top floors you have masonry wall, while in the bottom floor you have concrete wall. So you don't need this amount of strength. So you keep on reducing it, and the final resultant frame, when it is pushed, and you can see that the crack pattern is quite uniformly distributed from top to bottom. So this achievement you can see in more structural quantities also, where the base shear strength of the soft story frame has been raised upwards, and the interstory drift has been reduced. Of course, the interstory drift would be reduced to around 0.75%, which is considered to be the adequate requirement for Nepalese buildings, as we discussed earlier. So further details about these results can be discussed later on, but before that, I would like to show how this iterative algorithm worked. So as the number of iterations increases, the story stiffness keeps on reducing, because you open the frame, so the stiffness actually reduces, but the area of opening will increase. And when you compare the cost of the building actually reduces, because this concrete shear wall is more expensive than the frame with opened concrete shear wall. And comparing the interstory drift, we restrict the drift at 0.75%, and you can see that the soft story frame interstory drift has been reduced here. And ultimately, what we could say is a zone somewhere in this area can be considered as optimum. Depending on how much the landlord is willing to pay, is the zone, is the final solution. If the landlord is willing to pay a little bit more amount of money, then he can go for this. But if he is willing to pay a little bit more, and then he can go for this with a particular amount of opening. And if his requirement is larger opening, then he can go for another one. So this is a very customized solution, as you can see in these figures. And finally, we also have to check the dynamic performance of these frames, for which incremental dynamic analysis was adopted. What is incremental dynamic analysis is, you take the frame and you gradually increase one earthquake. Suppose you have a small earthquake, you scale the earthquake to make it big, and then you keep on increasing the size of earthquake, and finally let the building go into collapse and see what is the capacity. So how to see this capacity, at what earthquake did this building collapse, is a fundamental way of looking at the dynamic performance of the building. And for this, we took Kathmandu as the selected region, and according to their codal provision, 0.36 G is the designated hazard level, But then Gorkha earthquake had shown about 0.2 G already. And we decided to use Gorkha earthquake accelerogram for incremental dynamic analysis. But then the earthquakes was too long, and since we had to do large number of simulations, we decided to reduce the size of the ground motion. So for that, we took significant duration. Significant duration is the duration in which the maximum amount of earthquake energy which is released. As you can see in the figure, it is somewhere between it's somewhere between 50 and 100. So this duration has been considered, and we used this duration, and we scaled this earthquake ground motion to different intensities. Intensity is a ground shaking measure, and we have used JMA as an intensity scale. There are different other intensity scales such as MMI or MSK, etc. We used JMA because we're working in Japan, and in JMA we took 4 JMA intensity to 6 upper JMA intensity for scaling and for getting ground motions. We scaled the pseudospectral acceleration to obtain different ground motions as shown here. And then we applied it on 3 different cases of the frame that we have studied. So the first one is the frame without any infill, and the frame with normal masonry infill, and the frame which we obtained from our optimization algorithm and AEM. We use this frame, which is called as the resultant frame. So in all these 3 cases, you can see that we have gradually increased the size of the earthquake. And we can see that at 4 intensity itself, this soft story frame had collapsed. And this frame sustained even 6 minus earthquake, but had gone into collapse mechanism in 6 plus. And our resultant frame had sustained 4 and 5 minus, and 5 plus also with certain amount of damage, but it was showing some large deformations. And 6 minus also, it has gone into some large deformations, but it has gone into collapse in 6 plus. Of course, the shaking was quite high here, but as I mentioned earlier, life safety was the fundamental requirement of Nepalese people. I think I'm running late. I'll try to conclude within 5 minutes. So you can see this final JMA and interstory drift curve. While the soft story frame had collapsed in 4 itself, this optimized frame, the retrofitting solution that we obtained from our research, this frame and this fully infilled frame had performed even until 6 plus earthquake and had gone into collapse in 6 plus earthquake. So with this, we would say that this kind of retrofitting solution would provide adequate seismic performance at lower cost and would also give adequate usability for the landlords. And ultimately, this kind of a solution has to go into a code book. So since this research work was presented in Japan, so we had to convince the committee or the organizations and the evaluating committee of this research work that this can get translated into a code book as an annexure. We did not make a new code book, but the existing code book itself can have an annexure with 8 different clauses to incorporate this kind of a retrofitting solution. So this was mainly for demonstration purpose. with all the equations that we have mentioned earlier. And how to construct this practically is the next thing that I would be explaining. And for that, we take a very simple or a very typical soft story building, and we take a typical frame which has to be retrofitted. We get all the optimized solution, and we remove the shutter, we chisel the walls, and we drill 3 to 4 inch in the beam and columns, and insert vertical and horizontal bars, and if required we will grout it with epoxy resins, and then we surround the columns with horizontal rebars, place the formwork, and then use shotcrete to fill the concrete, and finally we get this frame. So to make this even more cheaper, one person cannot go for retrofitting on a day. So instead of that, as I mentioned in the previous slide, we may have to go for certain equipments like drillers, shotcreting. So we might need ready mix concrete, etc. So in the first slide or second slide, I showed you a photograph of a typical semi-urban street in Nepal. So if all these buildings decide to go for retrofitting on the same day, if they prepare everything, if they can prepare everything and keep, if they can make the, if they can go for retrofitting solution, they can consult local engineer and get the resultant frame and the corresponding retrofitting scheme, and they can procure adequate formwork, etc. And then they can place the formwork and keep it ready. Few ready mix concrete trucks can run into the street in the same time, and then fill in at the same time and leave. So in this way, the cost can be reduced. And to ensure this kind of retrofitting, we also need to propose how this work can be institutionalized and who will be the stakeholder for this. And for that, we first need to understand the social problem thoroughly, which we have tried to understand in this research work. And then we had to do a comprehensive research work and come up with solution. Of course, this research work has been done until this point, but we have to extend this to address various other problems involved around this method. And then once that research part is sufficiently matured, we have to take this research work to the socio-academic bridging institutes like NGOs, etc. And then they will create awareness among house owners and community people, like Nepal is already doing in rural areas, which will create an appropriate demand. And they will also create awareness among the vendors on required raw material for this retrofitting. And at the same time, these socio-academic bridging institutes should increase the capacity of masons and engineers as well. And they will be the source for technical supply, and the vendors will be the source for product supply. And finally, government should institutionalize the whole system of this retrofitting game, and finally we can have a retrofitted building without soft story problem. And the implementation strategy should be from bottom to top and not from top to bottom. We have to create an awareness program. We have to increase the demand, and for this, different kinds of stakeholders are responsible, such as political leaders, house owners, community people, material suppliers, vendors, schools, universities, recently apps, social media, etc. And then the supply capacity has to be handled by engineers, masons, house owners, contractors, consultants. And finally, the supply mechanism has to be dealt by the municipality or government authority to institutionalize the whole system. Finally, I would like to conclude by saying that the failure to solve soft story problem in Nepal is mainly due to high cost and due to lack of usability in the solutions that are proposed so far. And in this research, we have provided a numerical solution, numerical optimization scheme. We've developed field survey forms to study the problem comprehensively. We conducted enough field studies in Nepal to understand the socio-technical aspects in the dimension of soft story problem. And we implemented sequential quadratic program algorithms in applied element method. We did a capacity assessment to obtain or understand the capacity of our resultant frame with the ideal case. And we also propose guidelines for implementation, construction, and design. So the advantage of this method is that it has stakeholder involvement. So the stakeholder can propose what would be the width of his shop after retrofitting and how much would be the cost that he could afford. And the solution that we have provided is locally available because we are proposing solution with regular construction materials, which would be available in Nepal, even though it is imported. And this solution is a standalone retrofitting solution. So it does not affect the other retrofitting solutions. So therefore, you can use this retrofitting solution and then still re-strengthen your building for other different deficiencies related to seismicity or any other disasters. Of course, this also has some limitations. We are focusing on buildings where the dominant failure mode would be soft story building. But from our understanding, we have seen that all these buildings have a significant amount of soft story problem, because I have physically touched the frames and I have seen the capacity of the columns to be very, very low. And in future, we would be working on a more comprehensive pre-assessment method for capacity assessment, and we will also do some 3D modeling of this method, and we will also do experimental verification. We will do a pilot implementation of this project in field, probably in India sometime soon. And I would like to say that my student has received an award from the department for his research work. This was considered to be the best research in 2019. Thank you. And oh, this is about me, but since there is no much time, I would like to stop here and give the mic back to Dr. Rajaram to take questions.